In this video, we're going to be looking at the first section of topic 17, which is the Principles of Transition Metal Chemistry, and this is part of the Year 13 IAL course from Edexcel. So there are quite a lot of learning outcomes in this. We're going to specifically be looking at the D block elements, which are our transition metals, looking at their electronic configuration and how that can be affected by oxidation number, what we mean by ligands and how these are then arrange themselves and bond into the transition metal. We're going to look at why these are coloured and understand where the colour comes from and why some transition metal compounds have a lack of colour. Looking at different types of ligands, in particular monodentate, bidentate and hexadentate. And then looking at the different shapes of transition metal complexes and introducing a new shape known as square planar, and lastly looking at haemoglobin. So first of all, what are the transition metals? Well, these are elements that are in periods 4, 5 and 6, and they are between groups 2 and 3. So it's this section here in the yellow one. And these are known as the D block elements because their highest energy electron is found in a D orbital. Remember, groups 1 and 2 are your S block, and groups 3, 4, 5, 6, 7 and 8 are your P block elements. We define a transition metal as a D block element that forms one or more stable ions with incompletely filled D orbitals. Now that's very specific, and that's something that comes up in exams where it asks you to specify how we define a transition metal, and we should have these incomplete D orbitals. They have very specific characteristics such as solids, they are high melting and boiling points, they typically act as catalysts, and that's something that we'll talk about in 17C, and they have very specific reactions. In this topic, we are only focusing on the period 4 transition metals, so we're only looking from scandium to zinc. Anything above that, so yttrium to cadmium and hafnium to mercury, is out with the purview of this course, so we're only looking at period 4. Now we can look at the electronic configurations of these transition metals, and both the elements and their ions can be written using our SBDF notation, and we covered that all the way back in topic 2, so if you're not sure you might want to go back and have a look at it. And remember, we fill our orbitals in a very specific way. So if we have vanadium, for example, we start off at the 1s, so 1s2, 2s2, 2p6, then we move to the 3s and 3p6, and then we fill, remember, the 4s first, so that would be 4s2, and then we fill the 3d, which would be 3d3 for vanadium. And if we have anything beyond zinc that has electrons needed to be added, they then go into the 4p. But typically we will only be looking at 4s and the 3d. There are some exceptions to this rule, if you remember back again to topic 2, and the exceptions are copper and chromium, where they fill only one electron in the 4s and the rest into the 3d orbitals, and that's because we get, for the copper and the chromium, either a half or a full 3d subshell, and that provides it with a level of stability. So you can see that we have our electronic configurations, and we can draw in our SBDF notation, or we can draw in our box notation. And it is important that you can write out and draw any of these for scandium right the way through to zinc. Notice our copper and our chromium exceptions, where we fill the 4s with one electron and then the 3d. Now, when transition metals form ions, they lose their 4s electrons first, then they lose their 3d electrons. So that's very important. If we get something that is a 2+ ion, it's because it's lost the 4s electrons, and then we still have some ions, we still have some electrons in the 3d. And each element is very special because it can lose varying numbers of electrons. So this is a little bit different to what we've seen with our group 1 and 2 metals. Transition metals can have varying oxidation numbers, and that is quite unusual in comparison to group 1, which can only have 1+, and group 2, which has 2+. And transition metals that have particularly high oxidation numbers, so we can get up to a maximum of +7, they are usually found in a complex ion along with an electronegative element, and that's typically oxygen. So you'll usually find it connected with oxygen. And again, this is a table that you have to know. So you've got your titanium, could be 3+ and 4+, whereas vanadium can have 5 different states, and that's one that we'll talk about in more detail. It's particularly the fact that these all have different colours. Manganese is what gives you that high oxidation number of +7, and we see that for manganate. So KMnO4, potassium permanganate, contains this oxidation number of +7. But as you go further and further along the group, what you tend to find is that they lose less and less electrons until you get to the lower numbers of iron, cobalt, nickel, and copper, which will have a maximum oxidation number of +3. So when you get to the nickel and the copper, these will only lose the 4s electrons. They don't want to lose any of those 3d electrons. And the reason why they don't want to lose these is as we get from the iron to the copper, we get a much higher nuclear charge. And that increase in nuclear charge means that the electrons are much more strongly attracted to the nucleus. Therefore, they're less likely to be involved in bonding. Whereas for titanium to manganese, all of the 4s and 3d electrons can be involved in bonding because they're held a little bit less tightly in comparison to the others. So we get our varying oxidation numbers depending on what transition metal it is. And this is an important factor that we will come back to when we look at the reactions of these in more detail. Now we pivot slightly to talk about these complex ions and how they actually form. And these all use something known as a ligand. And a ligand is a species that uses a lone pair of electrons to form a dative bond with a metal ion. So the important thing here is that we've got these empty orbitals, whether it's a 3d orbital or a 4s orbital, and we can form a dative bond here. And when the ligands join with the metal ions, they form a complex. So for example, you could have something like iron, which has got a complex with water, and the oxygen donates its lone pair, and this actually happens 6 times. So we get an octahedral style shape, and we'll come back to the shapes a little bit later. But you can see that we're getting 6 dative bonds, each with the oxygen donating in a lone pair. And overall, this complex will have a charge, so we put our square brackets and the charge outside, and in this case it's a 2+. Now, why does this happen? Well, the very small ionic radii of transition metals, when they become ions, allows them to attract very electron-rich species. In other words, they attract the lone pair. And when they attract that lone pair, as we've said, it is forming a dative bond. So the most common example is actually water molecules that are present in aqueous solutions. So you may have heard of hydrated copper or hydrated iron, and this is because the water molecules are acting as ligands all around these transition metals. So the water molecules will form a specific number of bonds, usually 6, and they will make generally an octahedral structure. And we can explain this arrangement using electron pair repulsion theory, which we learned back in topic 3. So again, if you're not sure about that, you might want to go back and have a look over the electron pair repulsion theory, but we will discuss it further on. So compounds that are formed between these metal ions and ligands are called complexes, and they will typically have an overall charge. And they can be written in a chemical formula. And the chemical formula, we have an example here, but it follows the same sort of order each time. We have the cation, and then in brackets, we have the ligand. We then have a subscript with the number of ligands, and all of that is put into square brackets, and then we have our overall charge on the outside. So we've got the Fe, being our cation, the H2O being our water, 6 telling us I have 6 water ligands, and the 2 plus is the overall charge of the entire thing. And the number of dative bonds around that metal ion is known as the coordination number. So this complex would have a coordination number of 6. Now, there are lots of different substances that can act as ligands, but there are a select few that we have to know and be confident in drawing and naming complexes using these 4 ligands. So the 4 that we must know are water, which is H2O, of course. That is a neutral charge, and when it is in a complex, we call it aqua. Hydroxide, our OH minus, of course, has a charge of 1 minus, and when it's in a complex, we call it hydroxyl. Ammonia is NH3, that is neutral, and we call this amine when it's in a complex. Please don't get this confused with amine, which is an organic molecule. Notice that we have the double M here, so I'm going to pronounce this as amine, just so that you can clearly see the difference here. And then we have the last ligand, which is chloride, Cl minus, of course, being a 1 minus charge, and that is chloro. And if you notice, our negative ligands always end in O, so that tells us something about the charge. As with all other complexes and all other organic substances that we've seen back in GCSE and A-level, IUPAC set out some very specific rules about how to name these complexes. And you follow the same way each time. So you're going to have the number of ligands, the name of the ligand, the name of the metal ion, and then the oxidation number of the metal ion. If it is a negative complex, so the overall charge is negative, we put ATE. And if there are 2 different ligands, they should appear in alphabetical order. So if you have amine and aqua, the amine should come first because that is alphabetical. And we will also use prefixes to show how many ligands there are, so hexa, tetra, tri, or di, whichever one it is that you need to use. So an example would be this one here. So our FeH2O6 2+ is otherwise known as hexa aqua iron 2. And this can break down into 4 different parts. So the hexa tells us that we have 6 ligands. The aqua tells us that the ligands are water. The iron is, of course, the transition metal, or your cation. And the 2+ tells us the oxidation number of that cation. So we know that this iron has a charge of 2+, and because the water is all neutral, that is the charge that we get overall. So our 6 waters are completely neutral, so the overall charge is only coming from this iron. If you have something else that has a charge, such as FeCl, and you maybe have 4 of them, they're going to have 4 negative charges plus the iron, so that overall that would give you a 2-. So you need to make sure that you balance out all of your charges to work out the overall. If we have that FeCl4-, in this case we're using a 3, that would be tetrachloroferrate 3. So the 3 being the oxidation number, the ferrate being the iron, the chloro because we have 4 chlorides, and tetra telling us it's 4. Now, notice that the name is not iron, this time it's ferrate, and that is because it is negatively charged, so we have to use the Latin name. Now, there are only 2 elements that you may need to identify the Latin name for, and that is iron, which is ferrate, and copper, which is cuprate. A lot of the other metals are much more simple, such as nickelate, chromate, and vanadate. The chances of you being asked to name a complex in an exam are quite slim, but they do expect you to be able to identify them using their names. So you should be able to confidently name them so that you can then apply that in a question. Moving on to the colours of these complexes, transition metals have very specific colours when it comes to their complexes. And in order to know how these complexes actually arise, we have to think about 3 main concepts. The first one is the electromagnetic spectrum and the colour wheel, and this is something that you may have covered in physics at either IGCSE or at A level. We have to know the connection between colour, energy and wavelength, and we also have to know the electronic configuration of these transition metal ions. So we're going to look at each of these in turn. If we first of all look at the colour of complexes, so this is using our electromagnetic spectrum colour, and we then look at the visible section. And that visible section of the electromagnetic spectrum is made up of limitless numbers of colours. So these are all the colours that we see every single day. And they all appear between a wavelength of 400 nanometers, which is violet, and 700 nanometers, which is red. And this is the visible region, as I mentioned. So this is the one that we see. And as our wavelength is decreasing, our frequency is increasing. So we're getting higher frequency and therefore higher energy, whereas we're getting a decrease in wavelength. Now we can then use a colour wheel to help us figure out what we call a complementary colour. And essentially a complementary colour is one that is opposite. So what we actually mean by this is when white light, which is a combination of all the visible spectrum, when that is passed through a transition metal complex, some wavelengths are absorbed by the complex. So some of the white light has its wavelengths absorbed, and the emerging light will be the complementary colour. So for example, if you have a complex that absorbs red light, which is in the red region, its complementary colour would be on the border of green and blue, so that compound would appear green or blue. So we're getting the white light absorbing the red, and the colour that comes out that we see is then blue or green. If we have a substance that contains violet light, or absorbs the violet light, its complementary colour is yellow, so that complex would appear as an orangey yellow colour. So we have to understand that this absorption happens and it's the complementary colour is the one that we see. But then the question is, why does this absorption happen? And this is then to do with the energy levels. So we need to consider the 3D energy levels. This is what makes transition metals so special, because we're talking about the 3D. And we want to compare a solution containing copper 2 ions and zinc 2 ions. So the zinc solution is colourless, but the copper 2 is blue. And the reasons for this comes down to the difference between the energy levels. So when we look at zinc, what we see when it becomes zinc 2+, we have lost the electrons from the 4s, because remember when transition metals make ions, they lose electrons from the 4s first, and we have a full 3D subshell. So this zinc has 10 electrons in its 3D subshell, completely filled. If we compare that to copper, copper only has 9. So this zinc is colourless due to the fact that it is a completely filled 3D orbital, whereas copper is blue, and it is to do with the fact that we have this space in our 3D energy level, and we're going to explain why this actually happens. When we get our water ligands, or any ligand in particular, but if we use water as the example here, we get them attaching to the copper 2 ion, and when this happens, the energy level splits into 2 different levels with slightly different energies. So rather than them all being the same energy here for all the orbitals, it splits into a slightly higher versus a slightly lower. So your top orbitals contain your 3 electrons, which are at higher energy, and your bottom orbitals contain 6 electrons. And this gap now in our energy levels allows for something known as a d-d transition. And what that actually means is an electron in this lower energy here When the white light passes through that and we get that absorption from the visible spectrum, that electron can be promoted up to that empty space. So this is why zinc doesn't do this, because it's all completely full. Whereas for copper, it has this space to allow an electron to move up to that energy level. So when the electron is promoted, because it's absorbing that energy from the visible spectrum, we then get a difference here. So this DD transition happens. And the amount of energy that the electron absorbs depends on the energy difference between the two levels. And the bigger the energy difference, the more energy it absorbs. So our electron is absorbing energy as it is moving between those two d orbitals. And because of that, we then get this wavelength of light being absorbed, and the energy gained is directly proportional to the frequency of the absorbed light, or inversely proportional to the wavelength. So as the energy gained increases, so when you get more and more energy, that causes your wavelength of light to decrease. And that then gives you that absorption of the specific wavelength, and what then comes out the other side is what has not been absorbed, and that's the complementary colour that we see. So what we can see here for the copper is we now have this promoted electron. And for the copper, the difference in the energy level is quite small between these d orbitals. So that means that we get a low frequency being absorbed from the visible region, which is the red end of the spectrum. Therefore, the blue light is what is transmitted. And this is why we see copper as blue, because the ion has absorbed the red end of the spectrum. It's absorbed that radiation and absorbed that energy. And what we see is what's left over, which is the blue light. So copper will appear blue, and because zinc doesn't have this extra space in its energy levels for the d orbitals, it can't do this, so it appears colourless. Now moving on to the shapes of complexes. You learned, as I mentioned previously, back in topic 3 about valence shell electron pair repulsion, or VESPR theory, and you use this to explain the shapes of molecules. We can do this in a very similar way, but rather than talking about the number of electron pairs in terms of bonding and lone pairs, we are talking about the number of electron pairs donated to form the dative bonds. So this is just a slight difference. We've got our dative bond electrons, and that's going to be the same as our number of ligands, and we can have 6, 4 and 2 are typically the ones that we've got. And remember, if we have 6 electron pairs, that's octahedral. 4 electron pairs around the central atom is tetrahedral, and 2 electron pairs is linear. And your bond angles are going to be 90 for your octahedral, 109.5 for your tetrahedral, and 180 for your linear. So if you can't remember these, you might want to go back and have a look over them. Again, if you go back to topic 3, you can check back through the different shapes, but these are the 3 that you're going to have to know. And the most common shape of complex is an octahedral complex. So water, ammonia and hydroxide all form octahedral complexes. And this is because these are all actually quite small ligands. So there is space for 6 of them around the transition metal. When you start to get to the larger ligands, they become much bulkier, so they don't have quite as much space, whereas water, ammonia and hydroxide are all very similar in size. And each of them only uses one lone pair to form the dative bond. So whilst the oxygen of the water and hydroxide contain more than one lone pair, it only uses one lone pair to form that dative bond. And we sometimes call this six-fold coordination. And as we've mentioned, all the ligands are of a similar size because all of the electron pair donors are all in period 2 of the periodic table, because your donors would be nitrogen and oxygen, which are both in period 2, so they're of a similar size. And these are some examples of octahedral complexes, and you've been drawing these out since topic 3, so you should be fairly confident about how to draw them. If you remember, you've got your linear, or the bonds that are in the plane at the top and the bottom, and then you have 2 hash bonds and 2 wedge bonds to show that this is a 3D. So your hash bonds going back into the paper, your wedge bonds coming out of the paper. So you've got hexaaquamanganese 2, which is the first complex, tetra aqua dihydroxyl iron 2, so we've got 4 waters, and then 2 hydroxides. Notice difference in the name, with the tetra aqua coming first because that's alphabetical, and then the dihydroxyl. And then we've got hexahydroxychromate 3. And you can see each of them giving the different charge as well. So I would recommend that you do practice how to draw these. You must have the solids and hash bonds to show the shape. You must have the overall charge, which will depend on the transition metal ion and the number of potential negatively charged ligands. You have your structures drawn with your square brackets, and your water ligands, you have to show that the dative bond is formed with the oxygen, because it's the oxygen that donates the lone pair. So it has to be written as H2O if it's on the left-hand side, or OH2 if it's on the right. And we see that here in the centre, where our OH2 is written on the right-hand side because it's the oxygen that is donating the lone pair. Now, tetrahedral complexes tend to be a lot less common than octahedral complexes, and to be honest, you will only meet one of them, and that is the chlorine ligand forming with copper generally. So we get the copper with 4 dative bonds with the chlorine, of course, all at 109.5 degree angle, and that is a 2-. Now, chlorine is in period 3, or the chloride is in period 3. Therefore, it is a bigger ligand, so there's not quite enough room around the metal to make an octahedral complex. So these will make tetrahedral complexes. In terms of linear complexes, you will only meet one, and that is the reactive ion that is present in Tollen's reagent. And you've learned about Tollen's reagent back in topic 10 and in topic 15, and we know it is used to distinguish between aldehydes and ketones. Now, because silver is in period 5 of the transition metals, the explanation of why this shape exists in its reactivity is not covered in this course. However, it is important that you do know it as an example of a linear complex. So you have the silver in the centre, and we get dative bonds between 2 ammonias. And again, notice I'm showing that the dative bond is being made between the silver and the nitrogen, and this is a plus charge. So as I said, you don't need to know about why it forms this shape, just purely that this is an example of a linear complex. Now, a new shape that we can look at is known as a square planar complex. So this is one that you did not meet back when you did Vesper, but it's fairly straightforward. These contain ligands that are all at 90 degrees to each other. So if we think about it similar to an octahedral complex, but at the top and bottom, instead of there being a ligand, you have a lone pair. So an example of a square planar complex would be xenon bonded to 4 fluorines, or tetrafluoroxenon. And this is because The fluorine uses one of its electrons to form a covalent bond, giving the xenon 12 outer electrons. And because we've got the lone pairs that would be present here, so the xenon, rather than having 4 lone pairs, has its lone pairs split to join up with the fluorine, but we get that repulsion. The 2 lone pairs want to be as far apart as possible, and the rest of the bonding pairs form this square shape. So it is very similar to an octahedral, but we just don't have the bonds at top and bottom. They are simply just lone pairs. Now, a very common square planar complex that we should know about is called cis-platin. And cis-platin is very commonly used as an effective treatment for some types of cancer, in particular for testicular cancer or potentially for breast cancer as well. And you don't need to know why cis-platin forms this square planar complex. These are much less common than any octahedral or tetrahedrals, and it's actually not easily explained by VSEPR, by our valence shell electron pair repulsion theory. And so because platinum is in period 6, it is going to behave very differently. So you are not required to know why it forms this shape. You are just simply required to know that it does. And it actually forms the platinum bonding to an ammonia on its 2 wedged bonds, and then on its 2 hash bonds, and on its wedge bonds, it's 2 chlorines. And this is the cis isomer. Now remember, we can of course have a trans isomer where we get a change where we have one of each on each of the wedge bonds and the hash bonds. So this one being the trans isomer. However, the trans isomer is not as useful as the cis isomer. So the cis isomer, or cis-platin, your identical ligands are next to each other. And all we have to be able to do is just to summarise how cis-platin's anti-cancer action works. The full understanding is way beyond the aims of this course. It would potentially be touched on maybe in biology at A level, but nothing in detail of what we would need to know. We can summarise it by simply saying this cis-platin has an effect to essentially get rid of cancer as best as it can. Of course, it's not a cure for cancer, but it is a very effective treatment. So we know that all cells contain DNA, and during cell division, 2 strands of DNA needs to separate to form more DNA. And again, if you're a biologist, you should know this. The structure of cis-platin allows it to form a bond between the 2 strands of DNA, which prevents them from separating. So what it actually does is it takes the cancer cells that want to try and separate the DNA to form more, and it stops it. It pulls those 2 strands of DNA back together so that it can't replicate. And when it can't replicate, the tumour or the cancer cannot grow or spread. So cis-platin essentially acts as the barrier to this DNA replication that the cancer would need in order to be able to spread or to grow. Now, trans-platin, as we've just seen, is when the identical ligands are opposite to each other, and this is very similar to when we mentioned optical isomers, that the small difference in the structure can completely change the properties. This is much less effective as a cancer treatment, and it's also a lot more toxic. Now, cis-platin is not particularly good for your body, and that's why you get side effects when you have something like chemotherapy. However, the trans-platin is much worse. So when we're making this cis-platin and trans-platin, we need to make sure that we completely isolate the 2 things from each other so that we are only using the cis isomer as our cancer treatment. Now we're going to look at what we call a multidentate ligand. So everything that we have looked at so far has formed one dative bond, and we call that a monodentate ligand, where we have one dative bond. So that would be like your water, your hydroxide, your ammonia, and your chloride. We can get two other types of ligands that you must know. One being called a bidentate ligand, where we form two dative bonds, and one known as a hexadentate ligand, where we form 6 dative bonds. And in general, we will call these multidentate ligands, meaning they can form varying numbers of dative bonds with the transition metal. Now, you will only come across one bidentate and one hexadentate ligand. So the bidentate ligand is 1,2-diaminoethane. So you can see here the structure is we've got the ethane, but instead of the hydrogens at the end, we've added NH2 groups. And that NH2 contains the lone pair on the nitrogen, and that's what can form the dative bond. But because we have two of them, each of these can form a dative bond to the same transition metal. So it is bonding in two separate places. And when we represent this as a ligand, we generally abbreviate it to EN. So rather than writing out 1,2-diaminoethane every time, we'll simply just write EN. And you can see that the structures get very complicated. So you would never be asked to draw this in an exam, but you should be able to potentially identify that this is the ethylene diamine or the 1,2-diaminoethane. And when it uses the lone pair, each of the nitrogens attach onto the metal ion. So you've got one ligand here, a second ligand here, and then a third ligand here, each forming a dative bond to give you 6 dative bonds. So we still have a coordination number of 6 here. And if we were reacting this with a nickel complex that had 6 waters, we would be removing the 6 waters and replacing them with 3 ENs, and we would then get this difference in our equation here. So we'd be kicking out the 6 waters and the 3 bidentate ligands taking its place. You will only meet one hexadentate ligand, and this is called ethylene diamine tetraacetic acid, which, as you can imagine, is a very large mouthful to say all the time, so we're just going to call it EDTA. Now, you may talk about this potentially in biology. EDTA is used to stop blood clotting when you take samples of blood, and it's used for a number of other chemical uses as well, but it can act as a hexadentate ligand, meaning it can form 6 dative bonds. And that's a very, very useful and very actually amazing molecule. And what happens is we lose hydrogens on each of the 4 carboxyl groups, and then your nitrogen also has that lone pair. So when you lose the hydrogens, you get the lone pair being formed on the oxygen because we lose hydrogen ions. So the hydrogen leaves behind its electron, and we get a structure that looks like this. And now you can see that we have got 6 lone pairs, and we have 4 negative charges here that's been formed when we've lost those hydrogen ions. So this is written out as EDTA 4-. And each of these 6 lone pairs can form a dative bond. And again, you would not be asked to draw this because that is an extremely difficult diagram to draw. What they may ask you to do is to write out an equation. So we've got our 4 lone pairs in the oxygens and our 2 lone pairs on the nitrogens forming this complex. And you can see that the red lines are showing you the 4 different dative bonds that are being formed. And we have, again, if we use a hexa-aqua complex, we've got 6 waters now being replaced with 1 single ligand. So we're going from having 6 ligands to having just 1 with 6 waters also being removed. Now this then has an effect on the stability, and we link the stability of these complexes to the ligands that are attached to them. Now most complexes are actually particularly stable and they don't decompose. We've looked at decomposition of compounds such as the nitrates and carbonates, where we looked at polarization. This doesn't really happen. So these don't decompose particularly easily. And what we're really looking at in terms of stability is we're looking at how many ligands there are. And the process of reacting complexes to form a different complex, so for example, replacing 6 waters with the EDTA, is known as ligand exchange. And we will see quite a number of ligand exchange reactions when we look at topic 17b and we start to look at the individual reactions of transition metals. So if you take a monodentate ligand like water, so for example, if we have the water being attached to copper and I react it with a bidentate ligand, I'm going to make the complex with 3 ligands now, plus 6 waters. So my 6 waters being replaced by 3 of the EN ligands. So my total number of species has increased. I went from 4 species on this side to 7 species on this side. And if you think back to topic 12, increasing the number of moles that are present or the number of substances gives you an increase in total entropy. So when we get this increase in total entropy, this actually causes an increase in stability. So this is a very favoured reaction, and it is also, of course, a feasible reaction in terms of thermodynamics because we have an increase in that total entropy. So any ligand exchange to swap out a monodentate ligand for a multidentate, so like the EN or the EDTA, this is going to be a very favourable reaction. Now, the last complex that we have to look at in this topic is looking at haemoglobin. Again, if you've been doing biology, you will have seen haemoglobin before, but you may not have went into its structure in detail. We're not particularly interested in how it all works. We're looking more at the structure and then how that is affected by carbon monoxide. So haemoglobin is made up of 3 different parts, and the largest part is the protein. Along with the protein, there is also something known as 4 heme groups, and these are made up of carbons and hydrogens. And inside each of these heme groups, there are 4 nitrogens. And these 4 nitrogens form 4 dative bonds with the iron in a square planar structure. There is a 5th dative bond that is from the protein to the iron, and then we can form a 6th dative bond with the oxygen. And that is what allows the oxygen to be carried throughout your body in the blood. So that 6th dative bond that forms with the haemoglobin acts as the oxygen carrier. So if we were to summarise this in a diagram, we would have Fe2+, and we have the protein, and then we have the 4 heme groups, and we're only showing the nitrogen part of it. So these are all bonded together in a way that we don't need to know. What we are focused on is the nitrogen part of it, and these nitrogens each have that lone pair that is being donated, and then that 6th dative bond comes from the oxygen. And when it forms this complex, this is known as oxyhemoglobin. And we get 6 dative bonds surrounding the transition metal ion. And this is what acts as a carrier. So this oxygen can attach and it can be removed. So we get this sort of reversible type reaction that we can have here. Where this becomes a problem is when you have carbon monoxide. Carbon monoxide also has a lone pair of electrons. So it can act as a ligand and it can form that dative bond with the iron. The problem is, when you compare the strength of the dative bond with the haemoglobin and the oxygen to the carbon monoxide and the haemoglobin, the carbon monoxide is much, much stronger. And because it forms a much stronger dative bond, it is less likely to be removed, and that stops the oxygen from binding. And this is a ligand substitution. So we have the oxygen that would normally be attached sort of being removed and the carbon monoxide taking its place. And once the carbon monoxide binds, it is not easily broken. So this forms our carboxyhemoglobin, and it is an extremely strong bond. And as soon as that strong bond is formed, that haemoglobin can no longer carry oxygen. And if we get too much haemoglobin in our bloodstream being converted to carboxyhemoglobin, essentially there is not enough to be carrying oxygen to support life. In other words, that would be fatal. So to put it in sort of simple terms, the haemoglobin-oxygen dative bond is weak, so it is a reversible reaction, whereas the haemoglobin-carbon monoxide is a very strong dative bond, so that is not particularly reversible. Therefore, it can potentially stop the oxygen from binding with the haemoglobin and essentially stop our body from carrying the oxygen that we need in order to survive. As usual, let's finish off with some past paper questions. So these have been taken from a number of different past papers, or a combination of past papers, so I've not specified the particular year, but we're looking at when copper 2 sulfate is mixed with potassium iodide, the copper ions are reduced, and the products are a mixture of iodine and potassium sulfate in solution, and we also make a white precipitate of a copper compound. So we want to write the ionic equation for the reaction between the copper and the iodide. And we don't have to write any state symbols here. So we're going to have the Cu2 plus, and it's going to be reacting with the iodide. And we know that we are going to make iodine, and we're making a white precipitate of our copper compound. Well, this has to be the copper iodide because the potassium sulfate has already been used, and that's a spectator ion. So we are going to make CuI, and that is going to require balancing like that. So we have got 2 coppers plus 4 iodides, giving us 2 copper iodide plus iodine. And now we want to complete the electronic configuration for this metal ion in the white precipitate. So we are looking at the white precipitates being the copper, and we want to look at the electronic configuration. So we've got the 1s2 is already given. It's then, of course, 2s2, 2p6, 3s2, 3p6, and this is where we change. If you remember, for any ion, we are going to lose the electrons from the 4s, so we will have no electrons in the 4s, and in the 3d, we will have 10 electrons. And then we want to give a formula for a stable ion of an element in period 4, which is isoelectronic. So another substance that has that same charge as what the copper does. So in this case, it would be copper 1. So we want to have something that's isoelectronic. So we go to the 1 next to it, and that would be zinc 2 plus. We give that same electronic configuration. The aqueous copper 2 sulfate contains this complex ion that we can see here, and we want to state how these electronic energy levels of the copper 2 can change when the water ligands form this complex. Well, this is linking back to our colour, and we have our 3D orbitals are going to split into 2 energy levels. So we're getting our 3D, if you remember, splitting into that. So we get 2 slightly different energy levels. And then for 3 marks, explain how this change in energy levels causes complex ions to have different colours depending on the ligand. So we're not looking at the difference in metals, we're looking at if we were to add in a different ligand, why might it be a slightly different colour? So whilst the copper may always be blue, it could be different shades of blue. So there are 3 points here. The first point being the 3D orbitals split differently, or they split to different extents depending on the ligand. So it's not that we get 2 on top and 3 on the bottom, or 3 on top and 2 on the bottom. It's that that difference in the energy levels will change depending on what ligand it is. We then have electrons absorbing energy. Now, please bear in mind this is not the same as a flame test where we emit the energy. This is absorbing the energy of different frequencies or wavelengths, depending on how you want to phrase it, of different frequencies as they move between the orbitals. So as you get your electrons moving from the higher and lower levels, you're getting that electron absorbing energy, not emitting energy. That's emitting is in a flame test. And then what do we see? Well, the colour that is seen is the complementary. The complementary colour, meaning we see the colour that is left over after the light has been absorbed. Then we want to look at what shape this is going to be. Well, if it's got 6 ligands like the water, this is of course going to be an octahedral complex. And then this octahedral complex can then react with this 1,2-diaminoethane to produce a complex ion, and all the water ligands are replaced, but our coordination number stays the same. We now want to draw the structure of this. Now, although I mentioned that it's unlikely this would come up in an exam, I didn't say it was impossible, but it doesn't come up that often. The EDTA one, I've never seen in an exam. This would be the most complex potentially that you would get, but it's actually not as bad as what it looks. So you have the copper in the center, and you know you're going to have 2 bonds in the plane, 2 wedged bonds, and 2 hashed bonds, like that. And each of those is going to join in with the NH2, because that's where the dative bond is being formed. And then once you have that, it's just a case of combining them together. So then you're going to have a structure like that, and you can draw skeletal structures. That's absolutely fine. Or you can draw it out as the actual CH2s, and this would then join there, and then join there. So each of these points here are, of course, our CH2s. And that would be the structure that we would get. And of course, we have to put our square brackets around, and this would still be a 2+ complex because we don't have any charge on the 1,2-diaminoethane, whereas the copper still remains copper 2. So there's the answers to the past paper questions. Pay particular attention to this one, the 3 marker about the different colours, just so that you can see how the marks break down. That's everything for topic 17A, the principles of transition metal chemistry. In 17B, we will go into more detail about the specific reactions of the transition metals. So please do look out for those videos. If you've got any questions, please feel free to leave a comment below, and we hope to see you back soon.